All right, kids, here comes section 8.4. This is the area between curves with respect to x. The next section is going to be with respect to y. I'll talk about the difference between the two in a minute here. So finding the area under the curve. So far you've learned to integrate, and it finds the area between the curve and the x-axis. But what happens if you have a function that maybe you have a happy parabola over here, and then maybe you have another function. I'm going to call this my, I'm going to call it g of x. And then you have another function, maybe it's kind of like a cubic guy that goes like this. He's going to be my f of x. And so you see how they create an area between them that's right here, that no longer has the x-axis involved at all. Right? This is the area I'm looking for between these two curves. And you can see that I can't use a regular integral like I always have, because that would tell me the area between the curve and the x-axis, and that's not what I want. I want the area between the two curves. And so what you're looking at is the area between the curves is you have a certain value. This would be your a value. This would be your b value. I should put it down here on the curve. A, b. This is a. So you're looking for the integral going from a to b for, it's always the top function, f of x, minus the bottom function. So the big thing to remember is it's the top function minus the bottom function. Bottom. And that's going to be going from a to b. And that's really the formula. So you don't necessarily have to remember f of x minus g of x. What you do need to remember is this guy here, top minus bottom. Okay? If you're looking at finding these, so if I look at, we're going to be talking representative rectangles, which is a little different than what they do in the curriculum video, but this is going to come in handy when we go to find volumes. If I make a representative rectangle between the two curves, the top of my rectangle hits the top of the curve, and the bottom of the rectangle hits the bottom curve. It kind of gives me a visual of what's on top and what's on the bottom. And so in my inequality here, f of x has to be greater than g of x. In other words, f of x is going to be my top function, and g of x is the bottom. All right, hold on. Closing the door on the dog. So let's try some problems. This whole section is always going to be top minus bottom, because I'm looking at a representative rectangle that's vertical. And these are the ones that are with respect to x. The next section we're going to go with respect to y. And just as an FYI, then our representative rectangles are going to be horizontal. And it's going to be, instead of top minus bottom, it'll be right minus left. We'll get there, but just to give you a heads up that that's what's coming next. So here we go. Find the area of the curves of y equals x squared plus 2 and y equals negative x when x equals 0 and x equals 1. So they were nice. They gave me a picture. They don't always give you a picture, and then you need to create a picture or come up with some way that you can evaluate them. I usually go with the picture, but here we go. X squared plus 1, and it's going between x equals 0, well that's here, and x equals 1. So the area that I'm looking at would be this area bounded in here between these curves. Okay, so that's the area I'm looking at. If I make a representative rectangle, it's vertical. Looks like this. When we get into volumes and revolving things, these representative rectangles are really going to come in handy. So it's good for us to get used to doing them now. All right, so I'm going to set up my integral. The integral goes from my x values of 0 to 1. And I have the top minus the bottom. Well, who's on top? the square, the parabola, is on top. So x squared plus 2 is my top function minus the bottom function, which is the line, negative x, with respect to x. And so you just clean it up and do your normal integral stuff now. So you've got the setup. It's going 0 to 1 for x squared plus 2 plus x. That's a relatively nice integral, x cubed over 3 plus 2x plus x squared over 2, going between 0 and 1. We can keep going. That's going to give me f of b 1/3 minus or plus 2 plus 1/2 minus 0. And so I get my common denominators, which would be 6, and that gives me a final answer of 17/6. Now it is an area, it is units squared, but they didn't really give me units, so if you want to put units squared, go for it. If you want to leave it without anything, then you can leave it without anything. All right, here comes the next one. Now this time they did not give me a picture. Find the area bounded by y equals 2 minus x squared and y equals x. You actually are savvy enough to be able to graph this. You just need a sketch to see who's on top. You know that this is an unhappy parabola moved up 2. Okay, there it is. You know that this is the line y equals x. I should probably make this longer, hang on. Whoop. Because my y equals x looks like this. And so now the area that I'm looking at is the area between them, under the parabola, and above the line. Representative rectangle is vertical. Looks like this. And this time, I'm not quite sure what the x values are. They didn't give me bounds like they gave me right here. I knew it was between 0 and 1. So if they don't do that, then what you need to do is figure out those points of intersection. This is the symbol for intersection. It's like an upside down U. I need to know what this x value is and what this x value is so I can set up my integral. And so I'm going to set them equal to one another in order to do that. So I take 2 minus x squared equals x. Where do they intersect? Well, that's going to give me x squared plus x minus 2. Thankfully it factors. Mr. AP usually gives you something that is factorable. I get x equals negative 2, x equals positive 1. Does that make sense on my graph? Sure it does. I don't necessarily care what the y values are for this. I just need the x's so I can put my bounds together. All right, so it's going negative 2 to 1. The top function is the parabola. 2 minus x squared. The bottom function is the line. All right, and then I go and I make it a little simpler. Negative 2 to 1 of 2 minus x squared minus x. I can antiderivative that. That would be a 2x minus x cubed over 3 minus x squared over 2, going between negative 2 and 1. Plug in the 1, plug in the negative 2, and then you end up with an answer of 9 over 2. So if they don't give you the bounds, the points of intersection, then you've got to find them for yourself. That was what made that one different. Third one, now this one's going to be a bit of a challenge. Number 3. Set up the integral. In other words, they don't want you to solve it, they just want you to set it up. That's kind of cool. In the first quadrant that's bounded above by the square root of x graph, that's this guy, y equals the square root of x, we know what he looks like, and the line y equals x minus 6. And you might say, oh, easy peasy, lemon squeezy, but there's a problem. And the problem happens, let's look at those representative rectangles one more time. If I make a representative rectangle in this neighborhood, by the way, it does not matter where you put them, just in the neighborhood, That is going to be a different scenario than if I'm over in this neighborhood. Can you see why? This representative rectangle has the square root of x on top and 0 on the bottom, right? It hits the axis where y equals 0. But this one, the top hits the square root of x and the bottom hits the line. Do you see how that's different? This representative rectangle is going to have a different integral than this guy here, because the top is the same, but the bottoms change. Where do they change? Now this is important to us. They change right here, right? They change right there at 6. That's when my top is the square root of x, this is 0. My top is the square root of x, and then the bottom's the line. So I need to set up two integrals to figure this out. The first integral is going from 0 to 6. That one has the square root of x on top and 0 on the bottom. And the second integral has goes from 6 to 9. And that one has the square root of x on top, but it has the line on the bottom, and the line is x minus 6. All right, so then I just kind of clean it up a little bit. First one goes 0 to 6 for the square root of x dx. The second one goes 6 to 9 for the square root of x minus x plus 6. And again, they only wanted you to set up the integral. They did not want you to solve it out. So you've got to be careful when you're looking at these pictures. Is the representative rectangle consistent? Is the top always the one function and always the other function, the bottom? Always the top this guy, bottom's always this guy. Always the top this guy, bottom's always that guy. Where this one changed things up. So you got to be careful for those kinds of things. Look out for those. All right, that is almost the end for examples. Let me flip the page. There's a couple more. Number 4 is find the area bounded by the curves y equals the ln of x and 1/2 x minus 2. So what do they look like? Well, if I come over here and I draw, you know the ln of x. I think you know the ln of x. It comes up the y-axis and then goes off to the right. And then I have a graph of a line that is -2 with a slope of 1/2. So it takes 2 to get to the next point. It looks kind of like this. Nope. Need to make my ln graph a little longer so that they intersect. Okay. So as I'm looking at this one, the area that I'm looking for now is the area between them, right? So here it is. If I'm just looking at the equations, would you know which one's on top? And you can pick a point. If you choose any coordinate, say I choose the coordinate, I don't know, 1, and put it into these two equations, it's going to give you a positive. I think the 1 in here would give you a 0 out. If I have a 1 in here, it's going to give you -3/2, -1.5. And you could tell that 0 is taller, so this would be the one on top, and this one would be the smaller one. I think on the video, the curriculum video, that's pretty much what he did. He didn't necessarily get into drawing the pictures. I tend to like the pictures. Okay, so this one we're going to use a calculator on because I need to know these points of intersection. I need to know what that is, and I need to know what that is so I can set up my integral. So I'm going to go to my calculator, and I'm going to say, all right, Mr. Calculator, where is the ln of x equal to 1/2 x minus 2? You could graph the two of them, find the points of intersection. You could go to your solve menu and find the points of intersection that way. But you come out with these two values, x equals point, and you want to take a bunch of decimal values for this, 1.145566, and x equals 8.210933. Now look at the picture, does it make sense? Yep, 0.15145. Yep, 8.2. They're in the neighborhood. The picture looks good. All right, so find the area bounded. I'm going to go from the smallest x value is 0.145566, lower bound. Upper bound 8.210933. And I have the top. Oh, I didn't make my representative rectangle. The top of it is the ln of x. And the bottom is my line 1/2 x minus 2. And so I go to my handy dandy calculator, I put it in the calculator, and out pops, thank you very much, men inside, 8.784. That would be the area for that bounded region. Now here's the doozy of the day. The doozy of the day is this next guy, number 5. Number 5 says, all right, let this be the region, and it's bounded by 2 square roots of x and x squared over 4, as shown in the figure. If the line y equals k divides the region into 2 regions of equal area, what's the value of k? And you say, what the heck are they asking me to do? So I'm looking at just this region, and I'm thinking, well, geez, where is it split in half, the area? And I'm just going to guesstimate that somewhere in this neighborhood right in here. If I were to split it right there, that this area would equal that area. This is what they're asking you to do. Figure out what that is. What x equals k, what's the k value? Where does that split happen? So let's think of it kind of logically. If I think the area from integral from 0 to k, I don't know what k is, so I'm just going to use a k. And this part over here, actually they both have the same setup, right? If I do a representative rectangle on this side and a representative on this side, they both have the same tops and bottoms. Okay, cool. So top is going to be your 2 square roots of x. The bottom is the one that's x squared over 4. All right, second one, it has to equal, that area has to equal from k to, what's the x value? The x value is 4. K to 4 of the same top and bottom, 2 square roots of x minus x squared over 4. Right, where are the areas equal? They have to be equal from 0 to k and from k to 4. Top minus bottom. So, let's see if we can antiderivative this. This side is 2x to the 1/2. So it's going to be 2x to the 1/2 times 1/2. Nope, I'm wrong. 2x to the 1/2. It's going to be, I have to add a power on. Let me try again integrating. Can I integrate? 1/2 plus 1 is 3/2. So 3/2 times 2/3 minus 1/4 x cubed over 3. Whew, 0 to k. Right, so add a power on, divide by the power. Add a power on, divide by the power. You've got coefficients involved. So let's see if I can clean this up. This side's going to be the same exact thing. I'll clean it up over here. I have 2 times 2 is 4. X to the 3/2 over 3. And I have minus 1/12, 4 times 3, x cubed. Going this time from k to 4. All right, well, we're going to have to plug in a k. So what's that going to look like? Now I'm going to use my pretty one over here. If I put a k in here, this is 4k to the 3/2 over 3. This is going to be a k into this side, so it's going to be k cubed over 12 minus k cubed over 12. All right, that is plugging a k in. When I plug a 0 in, it's going to be zeroed out. Equals. Put a 4 in. The square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32. And so I end up with 32/3. 4 in here, oh goodness me. I think 64. I'm going to leave it as 64/12. Minus the k. Well, I did the k work over here, so it's a copy of that. 4k to the 3/2 over 3 minus k cubed over 12. Your job is to solve for k. And you're like, what on earth is this? So if I look at this, I have, I'm afraid I'm going to run out of space here. If I take and simplify this stuff a little bit better, I have, since I know I'm going to need my calculator for, I have 4k to the 3 halves over 3 minus k cubed over 12, forget about the 0, equals, all right, let's see if I can calculate this out fast here. If I have 32 thirds and I want to change it into 12, 32 times 4 is 128 twelfths. 128 twelfths minus 64 twelfths. And then I have minus 4k to the 3 halves over 3. And I have plus, negative, negative, plus k cubed over 12. Well, if I want to solve for k, I need to get all the k's on one side, right? So I'm going to take these k's and put them together. I'm going left. 4 thirds, it's going to turn positive. It's going to join up with the other 4 third guy. They become 8 thirds k to the 3 halves. K to the third over 12 comes over here, becomes a negative. So they join up, negative, and I'm going to have 2 of them, right? So I add them together, I get 2k cubed over 12, and they equal 64 twelfths. All right, so then I go to my calculator and I solve it out, right? What's k? So the calculator tells me that k equals 1.764. Does that make sense that that would be about the value, which is pretty much where we put it, right? Between 1 and 2, closer to 2. And that's the k value that would split it into 2 equal pieces. And so there you go. You've got, that's probably the hardest problem of all. Kind of makes sense though, if you set it up into your integrals and set them equal to one another, that you can find that k value. I'm going to do a couple practice problems. Here we go. First one's number 3. I have the line y equals x. I have the line 2 minus x. In other words, 2 is my y-intercept. My slope is negative 1. Put it this way. So these are what they look like. This is y equals x. This guy is y equals 2 minus x. And so I'm looking for the area bounded by them, and y equals 0. That's the x-axis. I'm looking for that piece right there. Now I'm going to blow it up a little bit. See that triangle that we're looking at? This side is 0. This side is 2, right? And this peak is at 1. If I were to do a top minus bottom in this representative rectangle, is this always the top in that whole area? And you say, no, it changes at this point. This would be a representative rectangle in this one. So I need to divide this into 2 sections because the top changes. All right, here it goes. And what do they ask me to do here? Sketch the graph, set up the integral, don't evaluate. Okay, cool. So I have one integral that goes from 0 to 1. And that has the x, y equals x value on top. And on the bottom, actually on the bottom it's 0, right? Doesn't it touch 0 on the bottom? I have to add that with the integral that goes from 1 to 2, and now my top is this line, 2 minus x, and the bottom is 0. And so fitting this together, 0 to 1 of x dx plus 1 to 2 of 2 minus x dx. So that one was different. The other ones, you're not going to have that change happen. I just wanted to show you that to remind you that sometimes the top and bottom change. So you got to be careful of that. So that was the first one I wanted to do. The second one is number 5. Flipping over, number 5. This one I had a hard time graphing. I literally had to go to my calculator to make this thing work right. Because what happens is you have a parabola. We all know what a parabola looks like, right? That's fine. But when I went to graph the cubic function, it looked, just in my sketch, it looked like the cubic function would be on top, and it's not. So if you don't believe me, go to your calculator and graph these and change your window so that it's just gives you a better window. It turns out that this guy is actually right there. Now, you could also take points and see if you put in like I don't know, put in a 2. You put on a 2, you'd have 4 for this, and you'd have 8 for that. So because of that, you can tell that, oh, I don't know. That's probably not true because it's not in the window of what you're looking at. You're only looking at values between 0 and actually 1. How do I know that? I'll tell you in a second. But if I put a 1/2 in, say I put a 1/2 in, 1/2 squared is 1/4. This is 1/8. So 1/4 is bigger than 1/8, and that means that this is the guy on top and that's the guy on the bottom. I went to the calculator to verify it, and there you go. I need to know what the points of intersection are, though. I need to know what these values are. Representative rectangle would be this way in there. And so if I take x squared equals x cubed and solve it out, x cubed minus x squared is 0, x squared comes out. I get x that's 0, and I get x that's 1. 0 and 1. They're my bounds. 0 to 1. We said the guy on top is x squared. The guy on the bottom is x cubed. Oh, dx there. They want us to actually evaluate these this time, so let me antiderivative. X cubed over 3 minus x to the 4th over 4. Going between 0 and 1 gives me 1/3 minus 1/4 minus 0, and that gives me a final answer of 1/12. There you go. There's number 5. Number 10 was next on my list. They gave you the picture. I'm very thankful for that. If I'm looking at this, though, what's on top changes and what's on bottom, actually this time the bottom changes. So if I have a representative rectangle in this neighborhood, there it is. Top is the parabola, bottom is the line, y equals 1. If I come over to this neighborhood, though, this neighborhood now has a top that's the parabola, but the bottom is the line. So where does it split? Where's the change happen? And the change happens at 1. All right, set it up. First one goes 0 to 1. Top is the parabola. That's 4x minus x squared. Bottom is 1, the line 1. Second one goes from 1 to 4. Top is the parabola, 4x minus x squared. And the bottom is the line y equals x, so x. Here's an issue, though. Is that true? Is what I just wrote actually true? And hopefully you're seeing that there's an issue. And the issue is, let me highlight it over here, right in this neighborhood. Because does the function actually go to 0? And the answer is no. It starts at some arbitrary point right here. So really my 0 is not a 0. That's not true. It starts a little bit to the right of 0. Where is that, you say? And so you want to know where 4x minus x squared equals 1. Now that's not going to be a pretty thing for you to factor, so you're going to go to the solve menu in your calculator, or point of intersection if you'd like that, and you get x equals 0.2679. So this bottom bound should be 0.2679. And now you got the right setup going on. One more issue. Where does the shading stop? It doesn't stop at 4, it stops at 3. There you go, let's double check it. First one goes from 0.2679 to 1. Second one goes from 1 to 3. And you've they top parabola, bottom 1, top parabola, bottom the line. Perfect. There's number 10. They didn't need you to set it. They didn't need you to solve it. They just wanted you to set it up. Alrighty. Let us try one more of these K value guys. Number 12. So, I'm looking at this. Let R be the region bounded by the curves. If the line y equals K divides it into equal regions, find K. So let's just guesstimate. If I have this picture and I want to divide it into 2 equal areas, I'm going to say it's kind of in that neighborhood. That's my guess. If I think representative rectangles, well, on this one, the top is a parabola, bottom's a line. On this side, top is a parabola, bottom's a line. Let's set it up. I need the area from, now I'm going starting at 2, right? From 2 to K. Top is the parabola, x squared minus 8x plus 16. Bottom is the line, negative 2x plus 4. Now that has to equal. The second one is going from K to, where does it end? 4. Same thing. Top is the parabola. Bottom is the line. So I guess I need to know what the antiderivative is for these. Let me clean it up just a bit before I do. I'm just going to put it down below here. X squared minus 8x plus 2 more is minus 6x. And 16 minus 4 is 12. So if I were to combine like pieces, that's what I'd have. Let me antiderivative that. X cubed over 3 minus 6x squared over 2 plus 12x going from 2 to K is supposed to equal, remember they have the same antiderivatives, x cubed over 3 minus, this should be a 3x squared, plus 12x going from K to 4. All right, so you're going to plug a K in, you're going to plug a 2 in, and you're going to end up in this neighborhood right here. Just for the sake of time, you can do the math out. But this will be 2/3 K cubed minus 6K squared plus 24K minus 8/3 minus 12 equals 64/3. I'm going to have to finish this problem because I think somebody's at my door. That's important. Okay, if I do this, I end up with, on the other side, equals 64/3. I end up with a solve for this guy, 2/3 minus 6 plus 24 equals, and I get all the k's on one side and the other pieces on the other. That's my job. 2/3 K cubed minus 6K squared plus 24K equals, and now on the other side I had the 64/3 plus 8/3 plus 12, right? Moving everybody left and right. Solve for K. Turns out K is 3. So that's going to be where that vertical line is. Does it make sense? Sure. It's in the neighborhood of 3. Life is good. All right. I'm going to stop with that one, and shoot me an email if you've got questions, and I will chat with you soon. See you in the classroom. Bye.